Shall start now. Yeah. Hello, everyone. Welcome to yet another talk by Antariksh Club of Vishwakarma Institutes, Pune. I am Rinmay Deshpande. On behalf of everyone, I welcome you all to this talk. And if you have any questions throughout this talk, please mention in the live chat. We will answer it at the end. And without further ado, let's begin for our today's talk. I'll introduce you to our guest speaker today, Dr. Preeti Kharb. Yeah, she's currently an assistant professor at the NCRA, Pune, and she has completed her PhD at IIA Bangalore and the Bangalore University, followed by a postdoctoral studies at the Rochester Institute of Technology, RIT, USA, and Purdue University. Her research is primarily related to the phenomenon of active galactic nuclei and particularly probing the jet physics in AGN. Some of the fundamental questions that she has attempted to answer, throughout her research are follows. The factors that are responsible for producing and launching the AGN jets and culmination of their propagation through the interstellar medium. And recently, she has even published a paper in Nature, which is really very commendable, and I congratulate you on that. So now let's begin.
Okay, thank you, Brinley. I hope everybody can hear me. My name is Preeti Kharb. Thank you for the introduction, Brinley. You've already told everybody about my institute, etc. So I hope you know that the National Center for Radio Astrophysics is the institute which runs the Giant Meter Wave Radio Telescope, also called GMRT. And GMRT is a telescope which basically observes astrophysical radiation at radio frequencies. And that becomes very crucial for the study my research area, which is on active galactic nuclei, because you will see that active galactic nuclei emit a lot of radio emission. And most of this radio emission comes in very spectacular jets, which I'll show several images, in fact. And those are the most exciting astrophysical images that you will ever see. And so without much more introduction, I just want to say that I will give you a brief historical perspective of AGN and tell you how the way we understand AGN, the different components that make an AGN, how we have come to realize those. And then in the end, I want to talk about what's the latest research on AGN. And that is happening through the Event Horizon Telescope, which is a millimeter wave VLBI array. So I'll talk about VLBI as well. And I'll share those results with you. And I'm sure you're familiar with the ESG results, which came out last year, and a recent one has come just a few months ago. So let me just start now. Okay, one sec. Right. Fine. So this is a picture, as you can guess, of our own galaxy, the Milky Way. And what we are seeing is now, this is also, of course, called Akash Ganga in Hindi. And what you can see are dust clouds. You can see the dust clouds here as we look from our Earth and solar system towards the galaxy's center. And the galactic center is where there is a supermassive black hole, which is the primary engine for an active galactic nucleus. So we'll talk more about that. But this is our Milky Way galaxy. Now, this is another image of a beautiful galaxy called the Whirlpool. And as you can see, you can't see individual stars here, but what you can see are stellar clusters, which you see as point sources, bright point sources here. So stars are what make a galaxy, along with, of course, gas and dust. You already saw a lot of the dust in the previous image of the Milky Way. And a typical galaxy has around 100 billion stars. Okay, so that's 10 to the 11 stars, like I mentioned here. And the second thing to note here is that you see there is an increased stellar density as you go towards the center of the galaxy. So the centers of galaxies are usually brighter. So this is where a lot of stars are. Now, it was in many years ago, in the 1940s, that an astronomer by the name of Carl Seaford noticed when he was basically studying these spiral galaxies, like Whirlpool is an example of. And so typical spiral galaxies, this is kind of a face-on spiral galaxy. And you can see, like I mentioned in the previous slide, that there is an increased stellar density towards the center. So the centers of these galaxies are brighter. You see also a lot of dust lanes, you can see here, in some spiral patterns. But what he found was that there was a set of few galaxies which were kind of peculiar in that, and this is one of those peculiar galaxies, that otherwise the galaxy itself looked very similar to any other spiral galaxy. You have dust lanes, etc. You have spiral arms, but what you see in the center is a bright point source. So it looks like a star. It's an unresolved point source, okay, which is really, really bright. And in fact, if you can see the screen well, you can see the diffraction pattern that is seen, right? And that is a sign of a point source, an unresolved source at the center of this galaxy. So this was the first, now these kind of galaxies are called Seaford galaxies, named after Carl Seaford. And the primary signature of this galaxy was a star-like nucleus. The second thing that he noticed when he took the spectra of these galaxies. So spectra is when you pass light, let's say through a prism or a slit, and how the light diffracts into its constituent wavelengths. And the presence of absorption lines and emission lines basically tells you about the composition of that gas which is emitting that spectra. So I'm sure you've seen the solar spectrum. You've seen the black lines of absorption that you see. What you saw in these Seaford galaxies were actually, instead of absorption lines, which is how a spectra which has absorption lines looks like this, which is what a normal galaxy, if you take a spectra of the center of the galaxy, for example, it's dominated by these absorption lines, which is telling you about the constituent gas, which is absorbing light coming from behind, let's say. But what he saw in these Seaford galaxies was emission lines. So you can see these bright, very broad, strong lines. Okay, and so this is the second characteristic of what the Seaford galaxies, which we now understand to be an active galactic nucleus. So these two properties, a star-like nucleus and a emission line spectra. So these are the two signatures often of a Seaford galaxy as well as an active galactic nucleus. So so the thing here to note is that this point source can be so bright, especially in the other types of active galactic nuclei, that it can outshine the entire galaxy. The star light from the entire galaxy can be outshone by this nucleus. It can even be 100 times more luminous than all the stars, the luminosity of all the stars combined in that galaxy. So for example, if you took a short exposure image of this galaxy, what you would see is just a star. You would not see the background fuzz. You will not realize it's a galaxy. You will think it's a star. And the second thing which I'll talk about in the subsequent slides is the fact that it's 100 times more luminous than the luminosity of an entire galaxy. What that means, a point source which is that bright, what does that mean? So this is another point source that actually was discovered almost 20 years later. And for 20 odd years, nobody really paid attention to the so-called Seaford galaxies. It was, they were considered peculiar, and it was just kind of noted down, and not much progress was made. And it was in the 1960s that another very interesting discovery was made. This was from Martin Schmidt, and so this is now what we call as a quasi-stellar object 3C273. And what you see is, of course, just a star. So Martin Schmidt looked at this star. He looked at the spectrum of the star, and the spectrum of the star looked like this. Now, to explain what this is what a spectrum, for example, would look like for some hydrogen gas, ionized hydrogen gas, in the laboratory setting. This is how the lines would be like. So there are these Balmer lines of, H beta, H gamma, H delta, etc. When he looked at the spectrum of 3C273, he saw a lot of emission lines which were completely unfamiliar. So it looked like they were from some elements which had never been studied before. It looked like a new discovery. But finally, what Martin Schmidt realized was that this was nothing but the same spectrum, the hydrogen spectrum, which was redshifted. And the redshift was around 0.158, which was the largest at that point. So this was an extragalactic source, an extragalactic star-like object. So most of the stars that you see, of course, are in our own galaxy. This was outside of our own galaxy and very far away. And so this was a discovery of what we call now quasars. 3C stands for the third Cambridge catalog. This was a radio catalog, and which was carried out in the UK. And this is the catalog number for this object. So 3C273 was discovered. And after that, it was realized how this was very similar to the Seaford galaxies that had been discovered 20 years earlier. And then that is when the AGN study took off. So now, so this is to summarize that Seafords were found in 1940s and quasars in 1960s. Now, the next thing which was found, of course, this is an image of the same object, 3C273. But what is now done is, this is an image from the Hubble Space Telescope. And what's been done here is the central light of the star-like object actually has been blocked by a coronagraph. And when you do that, suddenly you see the fuzz that makes the host galaxy. So then it's very similar to a Seaford galaxy. And at the same time, in the 1960s, radio telescopes had become operational. And we were able to now look at the sky at radio frequencies. And when this object, 3C273, was looked at radio frequencies, this is what was observed. So this is the center of 3C273, which will be here. But there is this jet. Okay, this jet. It's emitting in radio waves. So of course, the color doesn't mean anything. It is false color. The extent of this jet is huge. Actually, this jet is also seen in the optical. If you really pay attention, it's there in the optical as well. But the radio jet is longer and connected all the way to the center. And this would be several tens to, I think it was probably less than 100 kiloparsec, but several tens of kiloparsec. So kiloparsec is 1,000 parsec. Okay, and parsec, so to get an idea, one parsec would be, for example, the typical separation between stars. Okay, so sun and the nearest star would be like a parsec. So this is 1,000 parsecs. So this is tens of thousands of parsecs. Okay, so that is the extent of this jet. And some of these jets, as we've come to know, can be even 1,000,000 parsecs, so megaparsec. And a megaparsec is the typical size between galaxies, for example, Milky Way and the Andromeda, etc. So this is the extent. They're long linear structures, and these are called jets. So jets they're just phenomenal in terms of the power, the extent. They just go all the way. They leave the host galaxy, they leave the center, and just go to distances, touching the next galaxy. So here I wanted to also mention that I already mentioned that the point source, that there was an unresolved point source. And the point source is basically, it's a point source means that your telescope is not able to resolve it, right, further. So the resolution of these optical telescopes, and now HST Hubble Space Telescope, is of the order of a sub-arc second, right? So that already tells you it's a very, very tiny object. Especially if you scale it to distances of, let's say, 3C273, it's a very tiny object of the size of, let's say, the solar system. That is the region from which this light is coming. And the light, I already told you, it could be 100 times the light from the entire galaxy, which means that you have, in a solar system size region, you have 10 to the 13 stars. So in our solar system, for example, we have the sun. Now you have 100 So how much is that? 10 to, yeah, so I mean, whatever, you do the calculation. So a billion stars is 10 to the 9, and then you have 10,000 billion stars, right? So that is the number of stars you have in this very, very small volume. So there's something very extreme is going on in the center of this galaxy and the AGN. Okay. And so now the next slide is, okay, yeah, before I come to the what we think an AGN is, AGN are important. This slide is to show that AGN are not just interesting in themselves, they can actually help you study the universe. So for example, this is a image to kind of show you, let's say if you have a quasar, and this is where the Earth is, and light from the quasar is coming to you. The quasar has a typical spectrum, which I already mentioned. It has these strong emission lines, but in the intervening space, because this quasar is high redshift, it's very far away, all the hydrogen gas in this line of sight, could absorb some of this background light. So that's what happens in, for example, the quasars, their absorption spectrum. So they actually have these absorption lines, which is due to these intervening systems. It could be, for example, a galaxy. It could be a cluster of galaxies. It could be anything. And all that intervening material is kind of, intervening systems are kind of absorbing light from the background quasar. So you can actually study, by studying quasars, you can actually study the constituents of the universe. You can also see how the universe is evolving, because you can look at quasars at very, very high redshift. So the current, for example, the highest redshift quasar that is known is has redshift of more than 6 now. So which is, I think, when the universe was just like 10% of its current age or something. It was very young. So you can see all the intervening galaxies to that time by studying the spectra of this quasar. So quasars and AGN are important not just in themselves, but also to study the universe. So this is a cartoon, and I will tell you how this cartoon has come to be, and why a cartoon. The cartoon is there because we actually cannot see this. Okay, so this is a cartoon to show what we believe are the various constituents of an active galactic nucleus. Let me just go to the next slide, which is similar to this and tells you that the central region, whichever I'm going to talk about now, is actually hidden from us. We can't image it. We don't have telescopes which have that resolution, which can actually image the central part of an AGN. But we infer that indirectly through the spectra, through other wavelengths, broad a continuum emission from different wavelengths, etc. So I will be talking about how these different components have come to be. So let's look at the model of an AGN. So it's believed that the AGN is extremely luminous because the light is actually coming as gravitational potential energy is being released as matter falls into an accretion disk onto a supermassive black hole. So there is at the center, which is the driving force of the AGN luminosity, is a supermassive black hole. A supermassive black hole would have a mass which would be 1,000,000 to 1,000,000,000 times the mass of the sun. So it's a very, very massive black hole. And matter is accreting onto it through an accretion disk. Okay, there is an accretion here, which is pointed out here, an accretion disk. And this, as matter accretes onto the supermassive black hole, the release of gravitational potential energy is what is powering the high luminosity that you observe. And somewhere here in this region, outflows are being ejected. And these are the jets that I already showed you for 3C273. And we'll talk more about these jets in the next few slides. We don't know exactly how jets are formed. We have a general idea. But as you will see from the results of the Event Horizon Telescope towards the end, there are still a couple of open questions about exactly where the jets are launched from. Are they launched from the accretion disk? Are they launched from the poles of the black hole? So this is something that's still not settled. And we believe that there are these lots of gas clouds around here, which are these gas clouds are moving fast and around the black hole, etc. And these are the ones which give you those emission lines. So the emission lines that you see in the spectra are coming from these clouds which are moving around the black hole accretion system. So this region, which is very close to the black hole, is called the broadline region, and it gives the particular width. It adds a particular, or rather, the width of a line is explained by these fast-moving clouds around the black hole. And there are narrow lines which you see, which are probably from clouds which are further away and moving slowly, so they are narrower. So the Doppler widths are smaller, and those are giving narrow lines. So the narrow and broad lines are coming from these clouds. And so I already told you about the jet. We also believe that this central engine is probably obscured. So this orange thing that you see is some kind of a torus-like structure. And it's basically dust and gas, which is hiding the central engine. And there are reasons to believe that this is so. Based on the spectra of AGN. So because there are AGN with lots of different types of spectra. For example, there are some AGN which only show narrow lines in their spectrum. There are AGN which show both narrow and broad lines. So that these can be explained by the presence of this kind of obscuring torus, so that if it's oriented in the sky in a certain way, you will not see the central engine directly in some cases. Okay, so that is to explain the variety of spectra that you see in the inactive galactic nuclei. So now, based on all these studies, based on the spectra, we actually have good details. We have detailed numbers for example, the electron densities that these clouds have, for example. So we think that the broadline clouds have electron densities which are of this order, okay, and the narrowline clouds have densities of this order, etc. So the numbers are not something that I would like you to remember. It's just that these are numbers which we believe to be very close to the reality, based on extensive studies of the spectra of AGN. Okay, so these numbers we have, and we believe there is a torus. So this is the model of an AGN, which is the current paradigm. So now let me just tell you a couple of different discoveries that were made, which each pointed out to these different components of an AGN. So the first, of course, is the presence of a supermassive black hole. So now it's believed that supermassive black holes actually exist inside all galaxies, all massive galaxies. For example, the best example of a supermassive black hole in a galaxy comes from our own galaxy, the Milky Way. So Milky Way, this is a picture for a study which has been carried out by the SKEC UCLA group over the last 25 years, where what these astronomers have been doing is they are actually following motions of stars around the center of our own galaxy. And so these colored rings that you see are actual orbits of stars, and the star names are given here, S0, 1, etc. These are the names of the stars that have been followed. And now we actually have complete orbits of several of these stars. So you know how fast these stars are moving, because we have data. We have been observing them for years now. We know how fast these stars are moving. We know what is the radius of this orbit. So once you have that, you just need to use Kepler's law to tell you what is the mass of the object around which the star is moving. And so this, you can estimate that by m is equal to v square r by g. G being the gravitational constant, orbital velocity is v, and r, so this should be a square, sorry, and average orbital radius. So if you do this, this study has revealed that there is a supermassive black hole of mass 4.5 10 to the 6 solar masses in the center of our own galaxy. 1 million solar mass black hole exists in the center of our own galaxy. So the Milky Way is like a very ordinary galaxy, and we have many more massive galaxies in the universe. So we believe that they also have supermassive black holes in their centers. And while we cannot, for the distant galaxies, for example, so this is a set of images for another galaxy called M84, M for Messier objects, 84, the catalog number. And in these galaxies, apart from the Milky Way, we don't have the resolution to follow individual stars going around the center of their galaxies. So what is done instead is you follow the gas. Okay, you follow the gas motion. And so this is what's been done for this M84. And this is now the center of M84, which is imaged with the Hubble Space Telescope. And this is the spectra of that gas from the center. So this is the slit that was put on the center of M84. And what you see here, basically what you see here is motion, gas motion, which is redshifted and blue shifted, which is it would be redshifted when the gas is moving away from you and blue shifted when it's coming towards you. So you know there is rotation. And this very sharp increase in the velocity of the gas closer to the center. And this is a signature of a supermassive black hole. So something is very massive in the very, very center, which is making this gas move very fast in the center. So these kind of spectra have also been obtained for a couple of external galaxies. And for example, in M84, we have an even more massive black hole. So it has a black hole mass of 310 to the 8 solar masses. So it's almost 100 times more massive than the black hole in our own galaxy. Okay, and just for adding information, now black hole masses have been obtained by a technique called reverberation mapping, which is basically, the idea is this, that any change in the light from the accretion disk will then impact the light that comes from the broadline clouds. Okay, because broadline clouds are basically, the gas in the broadline clouds are basically ionized by photons which come from the accretion disk. So usually what is observed is there is a time lag. So any, let's say, sharp change in the brightness of the accretion disk, there is a time lag, and then the light from the broadline clouds increases. So you see in the spectral lines, and that lag tells you how far the broadline clouds are from the accretion disk. So again, it's the same idea. Once you have the distance of the broadline clouds, you already have the velocity of the broadline clouds, you can get the mass of the black hole. And that has been done for several AGN. So now we know that there is a supermassive black hole in the center of all AGN, all active galactic nuclei. Okay, so now let's come to jets. And I already showed you the jet of 3C273. What was found when the study of radio jets began was that if you took the flux densities, or the flux, the brightness or the flux from these jets at different frequencies, they seem to show a spectrum like this. Okay, spectrum meaning this is just basically flux density with frequency. So this is known as a power law. Okay, and so the continuum is like a power law. So at basically, as you keep going to higher frequencies, there is a characteristic slope of this line. So this is a way to define this curve. So flux density is proportional to the frequency to the minus alpha. So alpha being the slope of this line. And this now, because of this particular shape and the particular slope, we know that this is coming from incoherent synchrotron radiation. So the spectrum, the continuum spectrum of the radio emission tells us that this is synchrotron emission. And the other thing that completely confirms it is that synchrotron emission is theoretically supposed to be highly linearly polarized, but never more polarized than 75%. And that is exactly what we observe when we look at the polarized signal, the polarized emission from this light. So you can imagine what I mean by polarization, because you know that synchrotron radiation happens when you have electrons moving around magnetic field lines. So let me just come to the next slide, and that will probably make it clearer. So this is how synchrotron radiation is produced. So when you have plasma, where you have electrons, protons, positrons moving in regions with magnetic fields, uniform magnetic fields, let's say, then these electrons gyrate around the magnetic fields, and this gyration then produces synchrotron radiation. When these electrons are not very fast, then the radiation that is emitted is cyclotron radiation. So if, for example, in the case of cyclotron radiation, the frequency of gyration is given by this formula, which is magnetic field, the charge of the charged particle, let's say the electron, 2 pi, mass of the electron. When these electrons are relativistic, so that means the electrons are moving close to speeds of light, then the frequency of the synchrotron radiation then becomes the gyration frequency for cyclotron into Lorentz factor square. So there is a huge increase in the frequency of gyration. And Lorentz factor is basically 1 over square root of 1 minus beta square, where beta is the speed of, in this case, electrons divided by the speed of light. Okay, so then you have this. Whenever you have anything moving close to speed of light, relativistic effects come into play, and you have synchrotron radiation in this case. And because you have this particular geometry, as you can see along this magnetic field line, the emission that you get is polarized, is linearly polarized, okay, because of the geometry of the setup, the process. Okay, so now some nice pictures. This is an image showing 2 different AGN, active galactic nucleus, and this is let me just explain what is what. So the green emission that you see here is basically the spiral galaxy. So this is optical light that you get in the spiral galaxy. The red structure, that the red emission that you see here is X-ray emission coming from hot gas. The blue structure that you see here is radio waves. Okay, so what you see here is some kind of a bipolar outflow, but which is very tiny. So a Seaford galaxy also has a radio outflow, not just quasars, but this radio outflow is small, very small. So it's smaller than the size of the galaxy itself. Whereas on the other side, you see a source like the quasar 3C273 that I mentioned already. So here, the blue light is the optical light, is the starlight that you would see if you just observe this source through an optical telescope. And the red emission that you see is radio emission. Okay, and you see these jets, beautiful jets being launched from the center. This is a zoom in of the same image from the Hubble Space Telescope. And you see even a dust lane, a dust disk, you see the center, and then you see these jets. Okay, so the thing to note over here is that this is the size of the galaxy. This is an elliptical galaxy, but look at the size of the radio jets. So they go and they go and they go. They keep going. So these are much, 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 much larger. So something in the center is creating these really large scale jets, which are going to covering intergalactic distances. But unfortunately, this type of AGN is not as frequent as this type of AGN. So these are the more common AGN with small jets. But these very, very large jets is a small fraction, maybe 10-15% of all AGN are like this. But they are the ones which look most spectacular. So here is an image, a beautiful image of one of those radio powerful AGN called Hercules A. So Hercules A, this is the elliptical galaxy that you see. This is the host galaxy where the AGN is. The AGN is in the center of that galaxy, where the supermassive black hole is. And then this pink emission that you see is the radio emission. So you can see how large it is compared to the galaxy itself. This galaxy, in fact, has a smaller galaxy here, which is kind of infalling into the main galaxy. Because galaxy mergers is a very, very, is the most common phenomenon. Galaxies evolve through mergers. So they, it's the same. We have the Milky Way also has companion galaxies, and so does this one. And this companion is now falling into the host galaxy of Hercules A. So this it'll be good to note how complicated the jet structure is. You can see these wiggles, you can see some kind of bubbles, etc. So this is all seen in the radio. But there was a very interesting open question that has persisted in Aegean physics, is that the jets are primarily of two types. And this was first found in the 1970s by Bernie Fanaroff and Julia Riley. And what they found, as you can see in this, so these are two radio AGN. Now you only see the radio emission. You don't see the host galaxy emission. You don't see optical light. So basically, the optical light will be it'll be coming from this, this size of a galaxy, even here, same. Now you're seeing only radio. So as you can see very quickly, there are fundamental differences between these two structures. One of them has this very thin jet, and then it stops in some bright region, which is called the hotspot. And then there is this diffuse emission, like a radio lobe. It's called a radio lobe around it. On the other hand, you don't have a collimated jet in this source. You have kind of a broad jets which open up to give these kind of plume-like structures. So these two kind of distinct radiomorphologies was first pointed out by Fanaroff and Riley. And why they are so is still an open question. Astronomers have suggested that maybe there is there must be some difference, in fact, in their central engines. So the black hole accretion disk somehow is different. Maybe the black hole is like spinning, rotating faster in this kind of a source and slower in this kind of a source. Or is it that there is just much more, medium, the galactic medium or intergalactic medium, so gas basically, which is somehow stopping this jet from moving freely and making it lose its collimation. So it's not like collimated anymore. It's not like a fine thin jet that you see here. So it's still not clear why these morphologies are produced. And to answer this, I think that this would solve a lot of fundamental questions about the central engines themselves. So this is an important question in Aegean physics. So the next two slides are just to show some beautiful radio images and to point out to you how exciting these structures are. So for example, so these are now 3 radio images, of course, false color. And this is a radio galaxy, which is known as a double-double radio galaxy. So you can understand why. So you have the center here. This is the AGN. You have what look like hotspots, like what I showed you in the previous slide, an FR2 galaxy, Fanaroff-Rayleigh type 2 galaxy with hotspots. But then it doesn't stop here. It doesn't stop there. There is another hotspot far away. Not so, it's a little bit clear here, not so clear here. And then there is lobes here. So this looks like a galaxy which produced these large jets and then stopped for a while. Somehow the jet stopped and then restarted. So why that happened is still a little bit of a mystery. It's believed that maybe the galaxy ran out of fuel. Maybe there was no gas to be accreted, so the jet stopped and then restarted when there was maybe a galaxy merger happened and it somehow had more gas to accrete onto the black hole, and then you had a restarted jet. And this galaxy, for example, is like really curious. So these kind of galaxies are known as X-shaped galaxies. As you can see from the shape itself, it looks like an X. Similarly here, this is a really complicated morphology, as you can see. It almost looks like the jet is like twisting and, almost like precessing. So when a jet is precessing, it could mean that maybe there is not just one black hole in the center, not one black hole corresponding to that AGN, but maybe a second black hole. Maybe it came from another merged galaxy long ago, which has somehow that second black hole is influencing the first black hole, and somehow it is twisting, it's moving around the black hole, which is producing the jet and influencing it gravitationally. So the jets are not able to stay stable in one direction, so they keep precessing. So these kind of sources are very intriguing, and there's a lot of work happening right now in this area to understand what is causing these jets to be like this or this. or this. And of course, it gets even more complicated now. So this was a typical, an example of an X-shaped galaxy, which I showed you in the previous slide. So you see, it's a little bit like an X, or maybe a little bit like a Z, so a Z-shaped galaxy. And so there was a lot of, and for example, this is radio emission. In the inset, what you see are there are two galaxies here in the optical, which is not seen clearly. There is a dumbbell galaxy. So there are two galaxies interacting very closely. And it was believed that maybe the interaction of these two galaxies is influencing the radio jet to behave in a certain way. But now, recently, last year, there was a piece of work carried out by astronomers at using LOFAR. So LOFAR is a low frequency array telescope, which operates at 100 megahertz frequencies in Europe. And LOFAR looked at this galaxy and and this is what it found. So this is that X shape that you can see here, but there is so much more. So it's not anymore an X-shaped source. So these authors talked about how it's not an X-shape anymore. So the explanations that were given for source to be an X-shaped source because of interaction with a neighboring galaxy, etc., they have to be revised a little bit. So this is all research in progress. Things keep changing. New facts keep getting added, and that sometimes can simplify things, and sometimes it can even make it more complicated. The second source of radio waves, so I mentioned that the jets are synchrotron emission. There's another source of radio waves, and that is from the mechanism called free emission. So this is a cartoon to show free emission. So if you have, let's say, a positive nuclei, maybe it's lost its electrons, and electrons are moving freely in this plasma, then whenever it comes in, it gets affected by the field of this positive nuclei, its trajectory changes. And when that happens, there is photons are emitted. And these are, this is called free emission. Okay, because the electron is free before and it's free after this interaction as well. Now, this kind of emission also has a particular slope. Like I showed you for synchrotron, where it had a slope of, let's say, 0.7. This has a slope of 0.1. Okay, so when you look at the slope of, so what you have to do is you get the flux or the brightness of the radiation at different radio frequencies and see how it behaves at different frequencies, and then shape tells you what is the emitting mechanism. Now, this emission, interestingly, was the slope turned out to be like this for very famous radio galaxy called Cygnus A. Okay, so Cygnus A is a very large source, very much like Hercules A, and this is just the center of Cygnus A. So Cygnus A, it has these jets, just like any other radio powerful AGN. But what was found by these authors was there is an extended emission in the radio, which has a slope of 0.1, just like what you expect for free emission, in a direction which is perpendicular to the jet. Okay, and so these authors suggested that they have found signatures of what we in the AGN model we said a torus. These authors suggest that we are finding radio emission from that torus. So the size of this torus, one second, I can't see it. So several hundreds of parsecs. That was the size of the torus, which is has been suggested in the AGN models, but not typically observed at radio frequencies. So these authors claim that they are seeing radio emission from the torus. And so the alpha, the slope of this emission was 0.1. The slope of this emission, which is the jet, was 0.7, which is saying that this is synchrotron emission and this is free emission. So this is happening, as you can, the thing I wanted to point out here is the year. So this is 2019. This was last year. So all this is very much work in progress. So we are still kind of trying to, we're still kind of getting, ideas about what an AGN is. It's a field which is still evolving very rapidly. Now let's talk about another thing, is X-ray jets. Okay, this is another very, very relatively new discovery. And this happened after the Chandra X-ray Observatory was launched by NASA. And the Chandra X-ray Observatory, when it was launched in the 1990s, almost 2000, they were not expecting to see this. So what they did when Chandra just opened the camera ACIS, Advanced CCD Imaging Spectrometer, when that instrument just opened its windows to kind of calibrate the instruments, and it was looking at what it thought was a calibrator, which turned out to be a quasar. It was a quasar. Quasars are typically used for calibration because these are point sources. And so this particular quasar was its PKS 0637-72, where PKS stands for the Parkes survey, and these are basically the right ascension and declination of the source. So this is just telling you what the position of the source in the sky. And they just used this, what they thought would be a point source, to calibrate its instrument. And what they found was that it was not a point source. It was a point source with a jet. And this jet was long, very long, 100 kiloparsecs. Okay, so this is a long X-ray jet, and this was the first discovery of an X-ray jet from an AGN. Now, you may say, okay, so X-ray jets, we already know radio jets. So why is it, why is it interesting? It's very interesting because if the synchrotron emission, as you saw, has a very steep slope, right? So by the time you come to X-ray frequencies, the slope gets so steep that you should not get any emission at all. But you see a lot of emission. So what's happening? So here, just another image of an X-ray jet. So this is the radio galaxy picture A. So this is how it looks at radio frequencies, the red emission. And this is, when you look at this object in the X-rays with the X-ray telescope, this is what you see. So you see lots of emission from the center. You see the jet very, very clearly, which is not even seen as clearly in the radio image, at least in this one. Very bright X-ray jet. You see a lot of X-ray emission from the hotspot. And this is kind of a composite image of the radio and the X-rays. Yeah, so this slide is to tell you that what we have tried answering the question about the mechanism which produces X-rays. And this is not a settled issue. So for the radio, we knew that it's synchrotron emission, but the synchrotron emission doesn't work for most of the X-ray jets that you observe. And that's because, first of all, you for the typical magnetic fields that we believe exist in jets, those electrons should lose energy extremely fast. So over tens of years, they should lose energy and not emit any X-ray photons. But the fact that you see 100 kiloparsec jets, that means the electrons are active for 100,000 years, right? So why is that happening? So which means, if this is true, if synchrotron emission is the mechanism, then somehow you have to keep these electrons moving really fast. They have to be relativistic, moving at speeds close to speed of light, very far from the black hole. So that is very odd. Like, what is accelerating these electrons so far from the central engine? This is a mystery. And there are other mechanisms people have proposed, that maybe it is what is known as the inverse Compton mechanism, where maybe the electrons which are producing the radio photons then somehow upscatter the radio photons to X-ray frequencies and things like that. But none of these mechanisms, this is just to show that none of these mechanisms actually explains all X-ray jets. So the takeaway from this is that we do not really understand either jets or the plasma that makes the jets completely. Okay, now we're coming to the last part of the talk, which is now going to deal with VLBI and jets as they launch from the black hole accretion disk system. So very, very close to the launching sites themselves. So this is a cartoon, of course. This is just a drawing of what we think is happening. So you have the accretion disk, you have the black hole. So this blue emission is supposed to show the jet, and these lines, the white lines, are supposed to show magnetic fields. Okay, magnetic field lines. And it's believed that somehow these jets are getting a lot of energy from the rotational energy of the black hole itself. So the black hole is rotating very fast. It's got a very high spin, and that spin energy is being extracted through this the plasma that is being launched in jets. So energy and angular momentum is being extracted from a spinning black hole. So this model needs that the magnetic fields have to be initially poloidal. Poloidal meaning they would be like, like this along the jet. But because everything is rotating, then they will get twisted. And somehow these twisted magnetic fields then help not only in the acceleration of particles, which I was talking about in the X-ray jets, but also keeping these jets collimated. That means keeping them very linear, like linear structures. They don't open up. In this kind of a model, this model was proposed by Blanford and Znayak in 1977. This model, power can be extracted from the spinning black hole, and the power extracted is proportional to the magnetic field strength of, as well as the angular velocity. Okay, so the faster the black hole, the more the initial poloidal field, the stronger the jet, the more powerful the jet. So to actually check if this model works, you now have to go very, very close to the black hole itself. And the way to do that is with the technique called very long baseline interferometry. And this is a technique which works best at radio frequencies. That's because of technical issues more than anything else. It's only now that astronomers are able to do very long baseline interferometry at optical frequencies. Okay, so the idea here in this cartoon is shown here is that you observe, for example, some distant object like a quasar. Now these lines here are supposed to show the wavefronts, the wavefront of the light that's being emitted by the quasar. In this case, it's radio light. And this radio light is being intercepted by these telescopes here. These telescopes don't have to be close to each other, like the GMRT. They don't have to be in the same area. They can be in different countries. Okay, they can be in different continents. And all they need to do is that they have to observe simultaneously the radio waves from this quasar. And the data is recorded on what are called magnetic tapes. And the key here is that they have to be time stamped. So you have to know exactly when a wavefront arrived at what time. And for that, you need what are known as hydrogen maser clocks. So very, very accurate of the order of fractal of each radio wave. And then you record this data at these two separate telescopes. And later on, you get these tapes together in one facility, and then you play it back and correlate the data. So this is what's done in radio observations, is correlation of signals from separate radio telescopes. Okay, so this now you don't have to do it in one place like the GMRT. Now you can do it for radio telescopes which is separated by a large distance. And what this is doing then, if you remember, the resolution of a telescope is basically lambda by d. Lambda is the wavelength of the light. D is the diameter of the telescope. In this case, diameter of the telescope is actually the largest separation between the telescopes. So the further away your telescopes are, the larger the diameter of the telescope that you're actually kind of synthesizing. So because of this, you can really get very, very high resolution observations at radio frequencies. So this on the top is an array called the Very Long Baseline Array in the US, which has all these telescopes which are separated by large distances, and they work together like a VLBI array. They're not connected to each other by optical fiber, which is what happens in the GMRT. So they're not connected to each other, and then therefore you do this technique called VLBI. So before I show the very interesting results from VLBI, these are some formulae which you can maybe take home. Is that because now you come to regions very close to the black hole, everything is moving fast. The electrons are relativistic, but the jets themselves are relativistic. So relativistic meaning they are moving to speeds close to speed of light. The plasma itself, the plasma has electrons which are relativistic. The plasma has a bulk speed which is relativistic. When you have such a situation, then of course the special theory of relativity comes into play, and then you have these very extreme phenomena that are observed, which sound counterintuitive, but you can, of course, explain them through the study of a special theory of relativity. So the formula, the couple of things I wanted to point out here. One is that when this happens, when you have relativistic motion, when you have very, very fast jets, then the luminosity of the jet that you observe, the brightness, the how bright an object is, it's actually not what is intrinsically the brightness, but it's that multiplied by a Doppler factor 3 plus alpha. The Doppler factor is basically 1 over gamma 1 minus beta cos theta. Theta is the orientation of, for example, the jet with respect to our line of sight. Gamma is the Lorentz factor, which I already told you about earlier. 1 over minus 1 square root of 1 minus beta square. Beta is b by c. So intrinsic luminosity would be something, but what you observe is much brighter. Okay, and that's just happening because the plasma is moving very, very fast. The second thing that you would see is differences in the brightness of the jet and the counterjet. Counterjet is the jet which is, if you have a bipolar outflow, one part of it is coming towards you, one part is going away from you. And the relative brightnesses of this jet and counterjet are affected by the speeds. And so this R is a ratio of the brightnesses of the jet and the counterjet, which are given by this formulae. And so basically they depend on both theta, which is the orientation of the jet with respect to us, and the speed of the jet. So which gives very interesting effects. And the last thing is this formula which says beta apparent is beta sine theta 1 minus beta cos theta. Beta being the speed of the jet, the intrinsic speed of the jet, and beta apparent is what you see as an observer. Okay, so it's not the same that is actually there in the jet. You see something different, and this is given by this relation. So let me just now come to how it manifests itself. So here, this is a contour image now. Same radio images that I showed you earlier. I just showed you grayscale. Now I'm showing contour images. And you've already seen this kind of a source. You have the core, what is called the core, the bright point source in the center. And then you have a jet and the lobe. So what you can see immediately is you see one jet, but you don't see anything here. So what you see is one-sided jets. It looks like it's a one-sided jet, but actually it isn't. It's an effect of special theory of relativity, which I already showed you in the previous slide. That is just looks like that because the jet is fast. Similarly, this is 3C279. We'll end our talk by 3C279 because it's an interesting quasar. This has a core jet, and then there is some emission on the other side, but there is no jet. It's like there is no jet. It's like a one-sided jet. And this is the same jet. Now the center, the core, is now being imaged with the VLBI. Again, you see a core jet structure, but again, it's one-sided. So one-sided jets. I'll talk more about this particular jet. This is a result of the STR equations. Second thing is motion. I told you beta apparent was beta sine theta by 1 minus beta cos theta, which then ends up giving, it looks like when you do a VLBI observation of these jets, when you really go close to the center and you see these jets being, the plasma being ejected from the black hole accretion disk system, and you follow this plasma, then it turns out sometimes it looks like this plasma is moving at speeds greater than speed of light. So this is called superluminal motion. And of course, you know that cannot be true. It cannot happen. So it just appears like that. It looks like it's superluminal motion. So for example, here, these are actual images of the jet in M87, which I'll also talk about more. And you see you following individual knots in the jet. This is the jet, and you following individual knots. This is at radio frequencies. Actually, this particular jet shows superluminal motion even in the optical frequencies. But you follow these knots, and these knots then, and these are the years. It seems like the knots are moving at speeds 6 times speed of light. More than 6 times speed of light. But if you look at the relation, which I just pointed out in the previous slide, all you need is the beta, the actual speed of the jet will still be less than speed of light. Let's say it'll be 0.99 speed of light. But if the angle of the jet with respect to line of sight is small, let's say 10 degrees, it'll appear like the jet is moving at speeds of 6.9 times speed of light. Okay. So these are the special things that come into play because these jets are very fast. So now coming to the last part of the talk very quickly, the results from the Event Horizon Telescope. So now this is the same technique, the VLBI technique. I already told you the resolution of a telescope is lambda by d. So we have already, we have taken telescopes at the two extreme ends of the Earth's diameter. So you've already got a telescope which is the maximum diameter that you can get on Earth. You've got that baseline. So you fixed d. So how to now increase the resolution? What you do is make the lambda smaller. Okay, and that is exactly what was done for the Event Horizon Telescope. So instead of observing at the frequencies, for example, that the GMRT observes in several hundreds of megahertz or a gigahertz, 10 to the 9 hertz, you now go to millimeter waves, and then that immediately increases the resolution of your telescope. So the Event Horizon Telescope is again a set of several telescopes which observed at millimeter waves. And the main target for the EHT, or at least the most exciting target for the EHT, was actually the black hole in our own galaxy. So the idea was that we want to now look at the radio emission or the millimeter wave emission coming from really close to the black hole. You want to get close to the event horizon of the black hole in Milky Way. That was the aim. And so the gravitational radius of the supermassive black hole in the Milky Way is around 10 microarc seconds. So the resolution that EHT is able to generate and which produce those beautiful images which are coming up was around 20 microarc seconds. And that was because it was observing at 230 gigahertz. So this is obviously, this is also work in progress. The initial work was done with just 8 telescopes, but the Event Horizon Telescope is now extending itself. They're including more telescopes. And so that's increasing the sensitivity of your array. So you will be able to image even fainter structures very soon. So they observed the Milky Way, and they also observed M87. Okay, M87 is a much more massive galaxy far away. It's got a very supermassive, massive black hole, a billion solar mass black hole. It's further away, of course, compared to the Milky Way. And its gravitational radii, which is like the Schwarzschild radius of, which is gm by c square. Schwarzschild radius. So here, because the black hole is actually spinning, you use the gravitational radius, which is half of the Schwarzschild radius, and that is around 4 microarc seconds. So you are now really going to the center, the event horizon of this telescope. So the EHT observed both the Milky Way and M87, but they published, or there was a press release for the results of M87 because they're still trying to interpret the data for the Milky Way. And this happened last year. And I'm sure you've seen this beautiful image of M87, which is the black hole shadow. And so this is the image that they got at 20 microarc second resolution. They could see the black hole shadow in M87. And what you see, I'm sure you are familiar with how this image is produced. But basically, what I want to point out is that the fact that this looks asymmetric in brightness is because there is gas motion, which is relativistic. So Doppler boosting effects, which I mentioned, the formula which I told you about, the L intrinsic and L observed, that difference because of Doppler factor, that's Doppler boosting. So things look brighter because things are moving fast. So this asymmetry is because whenever you have matter moving towards you, that's Doppler boosted, and moving away is Doppler dimmed. And the fact that you see a circle like this is because light from the back of the black hole, like you can see here, is now being bent by the gravity of the black hole. And so you see this circle around that. Okay, so beautiful effects. And this observation has confirmed several speculations or ideas that we had about AGN. So this gives a boost to the Blandford's knife mechanism, in fact, for which has been suggested for AGN jets. This is broadly consistent with that. And there are several other things which this observation has confirmed. Now we have this beautiful montage. This is how we are now going from very large scale to very small scale. So this was how M87 image used to look like. This is, for example, if you looked at M87 with the GMRT, this is the kind of image you will see. Code jet structure, you see it's one-sided, just like I pointed out for other AGN. And that's because of Doppler effects, boosting and Doppler dimming. And then you keep going, you look at that with higher resolution. VLBA was the array I showed you, the VLBI array in the US. You look at that center of the core of M87 with VLBA. You see a core and jet structure. You see this limb brightening, which is also very interesting. You keep going higher. GMVA is a global millimeter VLBI array. You keep going to the center of this and all the way, and then you come to the black hole. So you come to the image that you got from the EHT. And now the next thing to do is, of course, all this has to be looked at in polarized light. So you can actually check if the idea that Blandford's Naik, you had these magnetic field lines which were twisting and collimating the outflow, is that really true? That's the next step. And then, so that's what astronomers are now doing, connecting this to that and in polarized light. So this is the final slide. And this is the most recent result from Event Horizon Telescope for the quasar 3C279. And I showed you this image in the one of the previous slides, that when you look at 3C279 with VLBI arrays, you see a core one-sided jet. And then you keep going to higher and higher resolution, which is what you get with the Event Horizon Telescope. And suddenly what you see is the jet, and then there is something which is extended, which is perpendicular to the jet. So this is the jet. And then you have something like a different direction. And so it is believed that this is actually the base of that jet. This is where the jet is probably being launched from, although this is something that astronomers are still trying to confirm. But if this, if this is true, then this would suggest that the jets are being launched from the accretion disks, right? So, and then there is if you can see, there are faint structures here which suggest that the jet is bending, etc. So all this is very interesting, and this is work to really understand what's going on in this particular quasar with the EHT still on. So this is the latest work, the most exciting work that's coming out of AGN physics. I'll stop here, and I'll be happy to take questions.
Yes, hello, ma'am.
Yes.
I'll ask you fewer questions. The YouTube
Sure.
live chat is full of questions. It was really a nice talk. The
Okay.
first question that I would like to ask you is by Mugdha. She's asking, are the centers of galaxies bright because of the stars orbiting around the SMBH?
Okay. So
Supermassive black holes.
So the centers of galaxies are bright. Normal galaxies are bright because there are just many more stars in the center of a galaxy. That's all. If that galaxy has a supermassive black hole, which is somehow accreting, accreting meaning mass is actually falling into the black hole, then that light is coming from the accretion disk itself. So the accretion disk is very bright at optical frequencies and ultraviolet frequencies. So if you look at that bright point source that we saw, is actually the accretion disk. So the brightness is actually the accretion disk when you have an AGN.
Right. Continuing on the topic of supermassive black holes, Tejas Rajuskar is asking, on what factors does the matter consumption rate of these massive black holes depend on?
Okay, so that is an excellent question. And I think not very easy to answer either. So what you're saying is that's basically the accretion rate, what is known as the accretion rate in AGN physics. What does the accretion rate depend on? So that I think is not trivial at all to answer. We know that as the accretion rate differs, the structure of the accretion disk changes. So when you have very low accretion rates, for example, the accretion disk somehow, puffs up and becomes a different kind, which is actually what you see in M87. It's a disk which is coming because of low accretion rates. Why the accretion itself is low? It could be lack of fuel. It could be something else. It could be a difficulty in somehow funneling, gas from larger distances to smaller distances. Somehow you have to bring that gas, which is further away to the black hole, all the way to the black hole. So if there is no mechanism to do that, then you will have a low accretion rate. So it's an involved question, and I don't know. Maybe I hope I've done a little bit of justice to that.
Of course, ma'am. The next question is by Sushil Ganesh. He's asking, does the Milky Way galaxy ever had an AGN? If yes, what effect did it have on the evolution of Milky Way?
Perfect. That's an excellent question. So, Milky Way, we believe, had an active had an active black hole. In fact, so it has a black hole, we know, and that black hole was once upon a time, we believe, active much more than it is now. And that is because when the gamma ray, the Fermi telescope, the Fermi Space Observatory, again a space observatory by NASA, when it went up, it found that there was a lot of gamma ray emission, which looked like there were like two bubbles above and below the disk of the Milky Way. And it looks like those bubbles may have been actually blown by some kind of an AGN activity in the center of the Milky Way. So this happened long ago. The Milky Way right now doesn't seem to be extremely active, but it probably was once upon a time.
Yeah, this is something new I haven't heard. Thank you, ma'am. The next question that I would like to ask is about the jets. What causes those jets and what are the components of those jets?
Again, a very good question. So composition of jets is again another open question in AGN physics. We believe that, so it is definitely, plasma. We don't know what that plasma is made of. It could be electrons, positrons, or it could be electrons, protons. So that that consensus on what exactly is the content of the jet content is still an open question. So that's all I can say. I think different studies are pointing out different things. Some studies suggest that maybe there are a lot of protons as well. Some suggest that there are not enough protons. It's just electron positrons. So it's not clear. It could be either.
Okay, ma'am. All throughout the talk, you said hotspots. What does those hotspots are exactly?
Okay. So hotspots are basically the last shock. You can say the terminal shock of a jet. Okay, so it's a shock as the jet kind of hits the medium around through which it's moving. So in the case of these large sources, it would be the intergalactic medium. So this is that surface where the jet is interacting with that intergalactic medium, and there is a shock there, and that shock is somehow re-energizing the plasma of the jet, and that is why it's giving this bright emission there. So there is some way to re-accelerate, let's say, the electrons and positrons or electrons and protons at that hotspot in that shock area, which is then making that region bright. So that's our understanding of hotspots.
Okay, I got it. The next question is by Parth Tulzapurkar. He's asking, is there a relation between the types of AGN and the galaxy morphology? Also, is there turbulence near the end of the radio jets?
Okay. Yes. The answer is yes. The most powerful jets, the ones which have these jets which leave the host galaxy and go to intergalactic distances, are almost always found inside elliptical galaxies. And the smaller jets are typically found in spiral galaxies. So there is a link between the host galaxy and the kind of AGN or the jet that's produced from the AGN. Why this is so is another question that is not answered. And this is usually known as the radio quiet, radio loud dichotomy. And so why some jets are very powerful and why do they always be inside elliptical galaxies? That's it's not very clear. It's possible that the larger jets are produced in more massive black holes, and which usually reside inside elliptical galaxies. So that's the first, and the second. The turbulence at the end of the jets? Yeah. So definitely, I mean, there is. If you look at, for example, you saw the image of Hercules A, and if you see also the image of Cygnus A, you will see that the hotspot is not just it's not like one hotspot. The end of the jet can sometimes have several hotspots, which means that the end of the jet is not stable. So there is some turbulence there, which then ends up, giving a very large, basically that working area, which is called the working area of that. The jet itself is large. It's kind of splatters, and there are several hotspots at the end. So there is turbulence at the end of jets. So that's the answer.
Yes, ma'am. Definitely, I guess, definitely the question is answered. I would like to take a final question, last two questions maybe. The next question is by Tejas. He's asking, what effects can these dense jets have on nearby stars or planets?
Again, okay, this is it's a really good question. I think there is a lot of debate in the literature in AGN physics. How much effect do these jets actually have on the surrounding media? So there is an idea called the AGN feedback, which is that somehow these jets really strongly impact the medium around them. So when they go through the galactic, first the interstellar medium, then the intergalactic medium, intercluster medium, they somehow influence everything: the gas, the stars, the planets, everything. So that is the idea of agent feedback. So there is then in that
Hello?
case, yeah, sorry.
Mridula.
Yeah. So agent feedback is actually suggesting that there is a very strong impact of the jets on stars and planets. But there are other AGN where somehow the jet doesn't seem to impact the surrounding medium to that extent. So it's probably different in different AGN, the impact that the jets have on the surrounding medium.
There is one last important question that I would like to ask. It is by Parth. He's asking if the electrons in the ISM continuously lose their energy near the rotating black hole, shouldn't they be trapped in the ergosphere?
Yes, that is very true. So they should have, but somehow something is accelerating them to leave, because you obviously see jets. So this matter, this plasma has actually left the ergosphere. So obviously it's energetic enough to kind of leave. And what that mechanism is again not 100% clear. For example, there are ideas that somehow there is the Fermi first order acceleration mechanism, etc. So there are several ideas which have been put forth to explain the energization of these charged particles. But obviously they are energetic enough to leave the system. So this is already happening. What is causing it is another issue.
Yes, yeah, I think we should stop the talk now. We are already over the bar. In the end, I would like to thank you, ma'am, for being with us throughout and taking time off your busy schedule. All the topics that you explained were really very insightful, and the last part regarding the black hole and even the jets, everything was very insightful. Really, thank you so much.
Thank you so much for having me.
Yeah. And in the end, for the viewers, I would like to specify that we would be having the live quiz set up at 8 p.m. So you could get a e-certificate through that. Please do participate in the quiz as well. Thank you.